Welcome to this demonstration of EcoStruxure Control Expert solutions to implement explicit messaging for Modbus protocol using the General Purpose Library, or for short, GPL. This is the second part in a series of two videos where we show examples on how to configure the GPL function blocks in the MC80 PLC for both Ethernet and serial communication. Please refer to the first video to review introductory concepts and examples on how the Advantys STB and TM3 modules were configured for this demonstration. Please bear in mind that this is a basic demonstration not intended to replace any formal product training. The user might also need to adapt the configuration shown to the actual project requirements. This presentation is structured in several chapters, each one started at the time indicated on this slide. The goal is to show examples on how an MC80 controller is collecting data from an Advantys STB island, from TM3 IO modules, and from an M340 PLC. This solution could help to easily expand the I/O capability of the MC80 PLC. Of course, this procedure can also be used for the M340 and M580 controllers as well, for both Modbus serial and Modbus TCP communication. The software for this demonstration is listed on this slide, using the most recent versions available at the time this video was prepared. And now we will configure the MC80 controller to use the GPL communication function blocks for Modbus TCP explicit messaging. Let's start with the main links for documentation, FAQs, and a great training video available on YouTube, as well as the link to download the Control Expert General Purpose Library version 2 from the Exchange portal. Once you log on to the Exchange portal, just do a search for General Purpose, and then you will find the link for the General Purpose Library v2 for EcoStruxure Control Expert. When you click there, on the landing page, you will have a tab for docs and videos in which you will find the release notes and the installation guide. That will give you a step-by-step guide on how to install the GPL library into Control Expert, as well as the project settings that you will need in your specific PLC program or application in order to use the GPL function blocks. Then you can click on the Additions and Pricing tab, where you will find the link to download free of charge the General Purpose Library version 2 for EcoStruxure Control Expert. Once you have downloaded and unzipped the GPL installation files, go to the EcoStruxure Control Expert folder in Windows and open the utility called Types Library Update. Here you will click the ellipsis button, and in the GPL communication folder, select the family.dsc file. Make sure it's going to be installed on the correct version of Control Expert and press the Install Family button. Once the installation is complete, you'll get a message confirming that it has been successful, and then we can proceed to open Control Expert to verify the installation. Once Control Expert is open, click on the Tools menu and Types Library Manager. Now locate the folder for Modican Libraries, General Purpose version 2, and you'll see the folder for the communication function blocks which have been installed. Now we can proceed to create a new project, and then we will select the model of the MC80 processor that we're using for our demonstration project. Once this is complete, we will proceed to change the project settings as recommended in the GPL installation guide. There are two sections where this is done: the Variables project settings, and then the Common project settings, all according to the GPL installation guide. Next, we will create a new communication network, which we are going to link to the Ethernet port of our MC80 controller. And we're going to call it Ethernet CPU. So now let's open the Ethernet CPU network, and in the security section, let's use the very first line of the access control list to enter the IP address of the laptop we're using to communicate with Control Expert. This is useful because once we have downloaded the program, we can continue communicating through Ethernet to configure the PLC. So let's go to the IP configuration tab, where we can add the IP address for our MC80 controller, as well as the subnetwork mask, which will be /24, and the gateway address. Once this is done, we can click on the validate icon, and then we can proceed to link it to the physical port on the CPU, going to the hardware configuration section. We will need to double click on the Ethernet ports, select channel 3, function will be Ethernet TCP IP, and the net link will have the name Ethernet CPU of the network that we just created. Now we can proceed to build our application for the first time. We just need to check that there are no error messages at the bottom and that the application in fact builds correctly. And we can also save the project in order to continue adding changes onto this file name. The reason I wanted to build right away at the beginning is to take note of the memory consumption available in the PLC menu option memory consumption, as it will be important to notice if the use of the function blocks of the GPL are going to require an important part of the memory of the MC80 controller. I would also like to show you where in the manuals you will find a detailed description of the function blocks that we will be using. First of all, in the client profile section, you will find the description of all of the input and output pins of the client function blocks, such as Modbus Ethernet client that we will be using. The port profile section is where we will find a description for the Modbus Ethernet port M function block, and of particular importance is the description of the public variables associated with this function block, as we will be requiring to use them in the examples that we will show. Lastly, in the appendix, here's where you'll find some examples and information about the work memory array, which is key for the operation of the communication function blocks. So I will go ahead and add two sections into our mass task. They will both be FBD type sections. First one I will call Ethernet Client, and is a section where I will actually add several Modbus Ethernet Client function blocks. The second one is going to be called Ethernet Port, which is where we will place a single Modbus Ethernet Port M function block. The important detail here is that the port profile function blocks must be executed after any of the client profile function blocks that are calling on the port function block. And in this demonstration, we're going to read and write to some Modbus addresses already available in an Advantys STB island. We're going to read the status of digital inputs in address 45,392, and we're going to switch some outputs available in word 40,001. So back in Control Expert, let's add our first Modbus Ethernet client function block using the function Input Assistant. You will find this function block in the Modicon Libraries GPL communication folder. Then you can scroll down and select the Modbus Ethernet client function block. And I recommend that using the Input Assistant, you change the name of the instance of this function block, which should start with the format equipment name underscore and then the exact name of the function block that you are adding into the project. This name and convention for the name of the instance of the function block is not really required for this demonstration, but I wanted to provide this as a best practice should you like to continue using the general purpose library in conjunction with the general purpose library for Aviva Plant SCADA, formerly Cytect, or Aviva System Platform. Now let's configure our first Modbus client function block, beginning with the start input. It will require a Boolean variable that will remain on during the operation of the function block. That's why for this demonstration I'm using system bit %S6, which is a periodic signal that will be turned on during half a second and then turned off during half a second as well. Going on for the read-write input, we're going to use a value of 0, as this is for a read operation. Bitword, we're going to use a value of 1, as this will be an operation on word, not a group of bits. Memory input, we're going to use a value of 0 for holding registers. Memory address, we need an offset of 1, and this is why we enter a value of 5391 to address Modbus register 5392 in the Advantys STB. Next, the device address is where we will enter the IP address of the field device, between brackets and quotation marks. And the priority input is going to define which queries are going to go out first through the communication port. We'll use a value of 3, and you'll see that in the manual there's a clear explanation on how this priority value is used. So typically the lower the value, this would be assigned to control commands, to write commands, and a value of 3 would be typical for reading data. Moving on, we're going to define the length of the request, which is the number of registers that are going to be read from or written to, starting from that memory address that we specified. And then the data input and output variable is the array where these values are going to be received. And then the size of the array must be greater or equal than the value of the length parameter. And then we can create the variable names for the output pins, which are basically used to monitor the operation of the function block. In other words, if communication is still in busy state, if communication has ended, or if communication has ended in error, if communication has failed. For faulty communication, there's also a fail code that is available and documented in the manual. There's also a statistics connector output that can be used as input information into another function block that will allow to calculate the number of messages sent, if it was good communication, bad communication, average time to send the message. And here you might notice a naming convention where the variable names are composed by a first part with an equipment name, followed by an underscore, and then followed by the name of the input or output pin. Last thing to do is to create the work memory array, which will be the same variable used for all of the Modbus Ethernet client function blocks linked to a common Modbus Ethernet port M function block. Now let's add a function block that will help calculate the statistics of communication. It will be found in the general purpose library communications folder, and it is called statistic counter function block. Again, best practice, instance name is the equipment name underscore and the name of the function block itself. Now, when we configure the variable name for one of the inputs of the statistic counter function block, we're just going to type in the variable name of the statistics connector output pin previously created for the Modbus Ethernet client function block. The reason for doing this is that not all GPL function blocks will accept the use of the link object to interconnect output with input pins. So with this technique, you'll be sure to be able to configure your project without any issues. So now let's add a second instance of the Modbus Ethernet client function block, and this time what we're going to do is copy-paste the first one that we configured. This time it's going to be used to write to change the value or the status of some outputs on an output module in the Advantys island. And as per best practices, I would recommend that you change the name of the instance for this function block. You can do it through the data editor, and it would follow the format of equipment name underscore name of the function block. And my equipment would be adv underscore write1 in this case. Next, we will modify this Ethernet client function block so it can write some registers in the same Advantys STB device, which means that we will transfer a value of 1 into the read-write input pin. As for the bit word input, it remains as 1 because we will write to a word type register. In memory input, we will use a value of 0 because we will write to a holding register and not an input register. As for the memory address, we will target register 40,001, which translates to an index of 0. This is the value that is transferred to the input pin. In the priority pin, we transfer a value of 1 because we would want to give a higher priority to a write operation. This means that queries with a priority of 1 are the first ones to be sent out of the communication port, and lower priority messages, such as the one for reading data, are sent afterwards. The length is correct at a value of 2 because we will in fact send 2 integers to the Advantys STB. Lastly, we have a couple of variables where the prefix is going to change from adv underscore read1 to adv underscore write1. And thanks to the fact that we are using a naming convention, this is very easy to do by simply right-clicking on the function block and using the Replace Variables option. Then we specify the pattern adv underscore read1 that will be replaced by adv underscore write1. This tool will then automatically create any variables that do not exist and will update all of the input and output pins that are affected by this pattern replacement. Lastly, the work memory variable will be the same that we used before because the second instance will be linked in this way to the same port function block, which is common to all of the Ethernet client function blocks that we are configuring. Now let's also copy and paste our first statistic counter function block. Now, another method to modify the attributes of a function block is to right-click on it and select the option Data Properties, where you can type in the required name for the instance in this first line of the general attributes table. Lastly, we can follow the same procedure used before with the Replace Variables option to replace the prefix of the variables linked to this function block. Now that we have configured our Modbus Ethernet client function blocks, let's go to the section of logic right underneath for adding our Modbus Ethernet port M function block, available on the GPL communication folder. Just have to scroll down and find the exact Modbus Ethernet port M function block, and the name that we're going to give to this instance is Ethernet CPU as equipment name, and then the rest is the name of the function block type. We will continue with our naming convention, and our equipment name will be Ethernet CPU underscore, and then the rest of the variable name is going to be the name of the input or output pin. Now, the variable that's going to be used for the work memory input and output will be the exact same one that we have already been using for our Modbus Ethernet client function blocks. This is precisely the way that the client DFBs are linked or related to their respective port communication function block. One more piece of information is needed to link the Modbus Ethernet port M function block with the physical Ethernet port on the MC80 processor. And this is done through a public variable that exists within the function block, and it's called the port address. We cannot modify its value directly in the data editor, which I'm showing on the screen, so a move function block must be used within the application logic to pass on a value onto the port address public variable. So on the input of this move function block, we're going to enter a string, which is 0.0.3, precisely a reference to the embedded Ethernet port of the MC80 controller. Then on the output, we need to add a reference to the public variable in the format name of the instance of the function block dot port address. Now we can proceed to build the changes in our application. And as we have no errors, we're going to set our address to connect to the IP address of the controller, and then connect to the MC80 PLC to transfer the application. Since the build has been done offline, it will be necessary to stop the controller in order to transfer the project. Once the program is transferred to the PLC and set to run, you will notice that the fail output in the Modbus Ethernet port M function block is true, and the same is happening on all of the Modbus Ethernet client function blocks. All the fail outputs are true at this time. Reason for that is that there is one more step needed in the configuration. We have to increase the size of the work memory array to be equal or greater to the wanted array size, which is automatically calculated by the Modbus Ethernet port M function block. In this case, 879 integers. So let's start by disconnecting from the PLC, as the change we must do has to be built offline. And then before going to our data editor, let's just take note of the memory consumption, particularly of the declared data, just to take a note of how this could increase. It is 11.1% at this point. Once in the data editor, we will locate the Ethernet CPU work memory array, and we will increase the number of elements to 1000, which is well above the minimum number of 879 which the application requires. Then we can build the application, which has to be done offline. And once the application has compiled without any errors, we can verify again what is the memory consumption for declared data, just to take a note on that to see if that increases. In this case, it's 12.7% for the declared data. Now we connect the controller in order to transfer the application. Remember, the build was done offline, so we will need to stop and restart the program. Once the project has been transferred to the controller, we will put it in run. And we will notice that the fail bit is no longer active on the port function block. And when we look at the client function blocks, the fail bit is not on, it's rather the end bit that is being activated after each transaction. Now we can create an animation table to monitor the information that is being read and written to the Advantys STB island, as well as some of the data for statistics purposes and fail codes. Once we have selected the variables in the data editor, right-click and initialize animation table. In the data that is being read from the Advantys STB, the first integer corresponds to the status of inputs on a digital input module. And there is already the first input that is cabled to a voltage, turning that bit on. We don't have any requests in error, and the fail code is 0, so communication is normal. And in our data to write, the first integer is actually changing the outputs in one digital output module installed on the system. Actually, I will turn on and off the bit of one of the outputs that is wired to the fourth input in the digital input module, and in this way we're proving that communication is functioning correctly. Other important information we can find here are the values in the fail code array. If we see all these values at 0, it means that there are no errors in communication. Otherwise, the values you will find here can be interpreted as per the user guide of the communications library. Lastly, we can inspect the statistic data for each one of the explicit messaging function blocks and compare them with the statistics for the port profile function block, which will show the total number of messages transmitted from the associated communication port, as well as the minimum, average, and maximum duration of the queries. Going on, we're going to continue the process by first disconnecting from the MC80 controller, as the changes we will do require an offline build. And the challenge is going to be to add a similar set of communication function blocks with Modbus Ethernet client to read and write data to a TM3 bus coupler system with the Modbus registers that have been previously configured. Going into the actual Modbus Ethernet client function blocks for TM3, we're going to replace the Modbus memory address. The device IP address must also be adjusted to end with 30. The length will be 13 elements of the data that is going to be read, and when creating the array to read the data, we also must make sure that the number of elements in this case is at least 13. Then the work memory array is exactly the same one we've been using before, and we just need to then add the rest of the variables that are now dedicated to read the data for the TM3 I/O modules. And the same is true for the variables that are required for the statistic counter function block for the TM3 read query. Following the same method, we would configure a Modbus Ethernet client function block to write data to the TM3 system using memory address 3501, device address 10.30 as before, with a length of 5 integers. All the rest of the variables have been created following the same naming convention. Lastly, there are 6 additional Modbus Ethernet client function blocks that have been added to write and read data to an M340 controller. What I would like to point out is that when reading data from input registers or input bits, you need to consider an offset to subtract on the memory address that you're going to use to configure the function block. So in the example on the top left, if you want to read data starting at input register %IW200, you must use memory address 199. On the top right example, to read input bits starting at %I96, the memory address that has to be used is 95 in the function block. As for the examples at the bottom, for write operations on memory words %MW or memory bits %M, there is no offset required, and the same is true for read operations on %MW or %M. To summarize, there are 2 details to consider when configuring the memory address input. First, you must use an index value, which happens to coincide with the memory addresses you will find in the TM3 and the Modicon controllers. However, in the case of the Advantys STB, addresses of holding registers start with 40,000, and you will need to subtract 40,001 to obtain the value of the index you will transfer to the memory address input of the GPL function block. Secondly, when reading input words or bit registers, which are %IW and %I registers in the Modicon controllers, you will need to subtract an offset of 1 to obtain the index to be transferred to the memory address input of the GPL function block. And once we have built and downloaded the application into the controller, we will be able to see what is the wanted array size calculated by the function block, in this case 2007. Then we will need to disconnect from the PLC and modify through the data editor the actual size of the work memory array. We will increase it to 2100 integer elements in order to exceed that wanted array size. Now we can proceed to build our application, and as before, we will check what is the percentage of free memory available, especially in the declared data section using the memory consumption tool. And we see that 18.5 of the saved data memory is used for the declared data in this case, so we're still within a good margin. And finally, we can connect to the controller and transfer the built application, and then verify that there are no communication failures shown in the port or the client function blocks of the GPL that we have implemented. And now, to complete our demonstration, we will review an example to configure the GPL communication function blocks for Modbus RTU, or in other words, for serial communication. And following a similar procedure for what we did for Ethernet communication, we will create a new section where we will put all of our Modbus client function blocks. And as before, we can use the function block input assistant and go and look into the general purpose library folder, subfolder communication, and we're looking for Modbus client basic as the function block, which is the one used for serial communication Modbus protocol. Then we can give a name to the instance following our convention, equipment name underscore name of the function block, and we start entering the rest of the information. Now, to simplify our example, I'm going to continue using system bit S6 to trigger the function blocks, except that the inputs are going to be negated in the case of the serial communication Modbus client basic function blocks. So whenever S6 is on, it's going to be Ethernet communication that's going to be active, and when S6 is off, it's the serial communication which will be triggered. Now notice that as you hover the mouse over the name of each pin, a tooltip will appear to remind you of its functionality. So in the case of the read-write pin, we're going to enter 0 for a read operation. For bit word, we're going to use a value of 1 because it's an operation on a word and not a series of bits. For memory input, let's use a value of 0. It's going to be a holding register, not an input register. The memory address is the first index of the Modbus registers we want to read. The Modbus address is the Modbus slave ID of our target device, in this example 2. Next, we're going to use a priority of 1, so the first messages coming out of the serial port are for this target device. As for the length, this is the number of Modbus registers that are going to be read from the target device. And then it's very critical that the number of elements in the array assigned to the data input be equal or greater to the value we entered in the length pin. Otherwise, when the target device sends the information back, if this array is not large enough, then the communication is going to be reported as faulty. For the work memory input, we're going to create a variable which we will call Modbus CPU underscore work memory, and it's going to be the same common variable for all of our Modbus client basic function blocks, and this is going to link them all to a single common port profile function block for the serial communication. Lastly, we just need to create the variable names, in this case for the remaining output pins of the function block. And as before, we can add a statistic counter function block to keep track of the number of messages sent successfully or with errors, as well as the time required for communication. And here we have a second example of a function block used to write values to the same target device, which has the same Modbus slave ID. Just make sure that the number of elements in the data array is equal or greater to the length parameter, which in this case is 3. And two more examples are shown at the bottom part of the section. Just wanted to illustrate once again that when you do create that variable for the array connected to the data input, by default, the array is only going to have 2 elements, so you need to adjust it to have a number of elements greater or equal to the value that is being passed on the length input pin. And we have one more function block to add for the port profile, and it's going to be done with a new section of logic, which has to be placed after the section where we have placed the Modbus client function blocks. We can then find the function block using the function block input assistant, and it's going to be called Modbus port M. Then we proceed to use an appropriate name for the instance of this function block, and once we have created all the required variables, one important detail to point out is that the address that's going to be passed on the public variable, port address of that function block, is going to be 0.0.0. A good explanation is presented in the user guide for the communications library, where it is explained that for this port address public variable, you would use a string with the format rack.slot.channel. And in this particular example for the MC80, 0.0.0 corresponds to the serial port of the MC80 processor. Then we can proceed to build the application and connect to the controller to send our compiled program. And as expected, the first time that the program is running, you will notice that there is a communication failure registered by the port function block as well as the client function blocks, because we need to adjust the size of the work memory array. And in this example, we will adjust this array to 1100 elements, which is greater than the value of 1089 elements calculated automatically by the port profile function block. And we can build, connect, and transfer the corrected application to the controller. And when it is running, we should not notice communication failures in neither the port nor the client profile function blocks. In this completed example, the 2 function blocks at the top are for reading and writing data to an M340 controller, the 2 at the bottom to TM3 I/O modules. And for this simple test, what I had prepared was logic in the target M340 controller, so when you write values to certain registers, they're going to be reflected in other registers that are being read by the MC80 master device. For the TM3 I/O modules, in a similar way, the MC80 master device is writing to the registers of the digital output modules, which happen to be wired to a digital input module. So that's how you see that the feedback is going to follow the value that is being written to the digital output module of the TM3 I/O modules. And of course, you can monitor the statistics of communication to see how many messages have been sent successfully or with errors, as well as the duration of the communication transactions. Let us finish with one more recommendation to correctly configure the GPL function blocks for explicit messaging in an M580 hot standby controller. The comment displayed on the screen is from the documentation of the general purpose library, specifically the communications function blocks and the Modbus and Modbus TCP explicit messaging function blocks. This basically has 2 implications. First of all, if we check the configuration settings for the M580 hot standby CPU, specifically in the hot standby tab, you can set up which sections of logic are going to be executed in both primary and standby processors. So the recommended setting in this case would be first section as the only list of logic sections that would be executed in both primary and standby. Secondly, when we look at the different sections of logic that have been configured for the mass task, in the very first one, we must not include any of the function blocks of the GPL for explicit messaging. This concludes our presentation, but before I bid you farewell, I wanted to also share a great source of information with pre-recorded webinars that can be useful for you. These you would find on the SchneiderElectric.com website localized for Canada. So after typing .se.com, please add /ca. And once you're on our landing page, please click on the Support tab and then look for the Innovation Summits link. Once the Innovation Summits link is open, you can scroll down and you will find these pre-recorded webinars, which you can filter with keywords such as syslog. You can also search for Builder, where I present the architecture builder software as well as some of the specifications for M340 and M580 PLCs. Also, if you type in the keyword cyber, you will find several presentations, including one of mine called Cybersecurity in the New Normal, where I do a quick review of cybersecurity applied to industrial control systems. Lastly, if you would like to learn more about new features in Control Expert, you will be able to find a webinar demonstrating the use of the read remote and write remote function blocks using multiple simulators. Many thanks for taking the time for watching this video, which I trust will help you during the development of your projects.